So, in the last lecture, in the last two lectures we saw spectral theorem version 1 and version 2. In version 1 the spectral theorem was written in terms of a projection valued measure, starting with a commutative C star subalgebra with identity of operators on a Hilbert space. We were able to identify the elements as certain integrals against projection valued measure. In the second version, which was more concrete, but then we had to pay the price of uniqueness, was to identify elements in A. So, these are actually operators to start with, but as concrete operators, that is multiplication by bounded functions on L2 spaces, right. So, L2 space with respect to a measure mu, which was semi finite. Okay. Depending on whether the Hilbert space is separable or not, we will be able to say a little bit more about this mu. In fact, we can make mu to be a sigma finite measure or even a finite measure if the Hilbert space is separable. Okay. So, we will start with such discussion and then go ahead and restrict ourselves to the case of a single operator, right. So far we have been looking at algebra of operators, right. It was a sister algebra of operators, and we have been saying elements there can be identified as multiplication operators or integrals against projection valued measures and so on. We will specify or we will restrict ourselves to the case of a single normal operator and look at the algebra generated by that normal operator and apply all that we have done so far, and then try to extract more information. Okay. So, let us continue. So, let me quickly recall the spectral theorem version 2. So, A was contained in B of H, right, and it was a commutative C star subalgebra with identity, right. So, that is what we had, and then what we got was that there exists omega f mu semi finite measure space, right, such that or well, moreover we have such that the Hilbert space is identified with L2, right. So, there is a unitary operator H from H to this L2 space, right, unitary, such that, well, there are too many such that there. So, there exists omega f mu semi finite measure space. Let me remove that, and operator u, which is a unitary, such that under u, after conjugation with u, everything becomes multiplication by bounded function, right. So, such that if I take any t, so u goes from H to L2. So, u inverse t u, right. So, t is going to be in the algebra A, then u inverse takes L2 to H, t takes H to H, and you will take it back H from H to L2, right. So, let us write it down here. So, I have H to L2 mu, this is my u, I have the operator t here which goes from H to H, and I have L2 mu, and question is what is the operator here, right. So, that is u2 u inverse, that is multiplication by phi t, right, where phi t is in L infinity. So, here it is multiplication by phi t. This is the second version of the spectral theorem. We also saw that omega is a disjoint union of copies of sigma, right. Sigma was the spectrum of A, right. Okay. And mu and the function phi t, which we got corresponding to the operator t, actually can be phi t can be taken such that phi t equal to t hat on each of these copies of right each of these copies. Okay. So, it is multiplication by t hat on each of these copies, right. So, this was the second version of the spectral theorem we proved. Okay. Now, just to quickly recap, we started with the cyclic case, we look at a vector v such that A v is dense, that means you hit v with all the operators in the script A and then form a subspace. It is a subspace because A is already an algebra and so on, and if that is dense we got one measure and then we transferred the operator t to multiplication by the Gelfand transform of t on the other side. If not, if it is not cyclic, you start with one vector and then look at the A v closure and then look at the orthogonal complement and continue, right. So, first we did the cyclic case. Okay, I will not go through the proof again because we did it in the last class. Then we chose, okay, so maybe next choose a maximal collection, right. So, choose a maximal collection of orthogonal vectors, V I in some indexing set capital I such that if H I equal to A V I bar. So, that is the cyclic subspace generated by the vector V I. So, essentially what we are doing, we are choosing arbitrarily the first vector V 1, look at A V 1 and take the closure and then take something which is in the orthogonal complement, let us say V 2 and then continue, right. So, Zorn's lemma will tell you that you can exhaust this. So, H I A V I and the Hilbert space H becomes direct sum of orthogonal direct sum of these H I's I in I. Okay. So, the indexing set can be uncountable, okay. And from here, so for each H I we got this measure mu I, right. So, and you sum up, right. So, we got this measures mu I for each H I, that means H I can be identified with L 2 of mu I and then you sum up, right. So, H gets identified with direct sum of L 2 of mu I, and when you use this identification as a unitary map, the operators t in A becomes multiplication by t hat on each of these copies, right. That is what we did. Okay. So, notice that you are summing up over an indexing set I. Okay. So, let us continue. So, we will start with some remarks. 1. If H is separable, if script H is separable, the indexing set I above will have to be countable, right. So, will be countable. Okay. Well, why is it countable? Because these are orthogonal, right, because remember H is the direct sum of H I's, they are all orthogonal subspaces, right. So, it is an orthogonal sum, and so if H is separable you can have only countably many orthogonal vectors, right. So, this is I in I. Okay. So, it will be countable. Now, if it is countable, so let us say it corresponds to V 1, V 2 etcetera, V 3 and so on, right. These are all orthogonal to each other, right. And remember the measure mu I is such that the norm of the measure mu I or the total variation measure is equal to the norm square of V I, right. And so, if you choose the vectors such that sorry not square, the norm itself, right. Okay. So, if you choose the vectors V I, so remember if you choose a vector let us say vector V 2 orthogonal to V 1, any multiple of V 2 is orthogonal to V 1, right. So, I can multiply V 2 with anything. So, I can choose it so that the norm is whatever I want. Okay. So, choose these V I's, choose this V I such that summation norm V I square is finite, right, because I is countable, right, because it is countable you can do that. So, that would mean the total measure of mu, right. So, mu is the sum of mu i's, right, and so mu and each of them has the total measure norm V I square. So, when I add up I am getting a finite sum. So, the measure mu you get in the earlier thing can be finite, right. So, hence the measure mu in the second version of spectral theorem, is finite. Okay. So, when the Hilbert space is separable, these are quite nice, and we can say that it is it is a finite measure. Okay. And so keep that in mind, most of the time one deals with separable Hilbert spaces. So, the spectral theorem says that the realization of these operators as multiplication operators on a finite measure space. Okay. That is one. Note that there is no uniqueness involved here, because the V i's can be chosen in any way you want, right. So, it will depend on what V 1 is and what V 2 you choose and so on. Okay. So, there is no uniqueness in this measures mu I. So, in this representation where H is identified as L 2 of something, the mu can change, okay, but it cannot be completely arbitrary. We will see that when you change the mu, you are not going to get anything completely wild, you will get something which is absolutely continuous, mutually absolutely continuous with respect to each other. Okay. So, you do not have much room, but it is possible to change the measure. Okay. So, note that this representation depends on the way V I are chosen. Okay. So, essentially no uniqueness, that is what I want to say. So, no uniqueness in the, unless the projection valued measure which was unique, you do not have uniqueness here, okay, no uniqueness. But it is not a serious issue. You will see that if you can only change it to something which is mutually absolutely continuous with respect to it. Okay. So, as a consequence of this version of the spectral theorem, we will strengthen an observation we made earlier. Okay. So, we will strengthen an observation we made earlier. Okay. Okay. So, recall that if f n converges to f pointwise and bounded, right. So, that means f n x converges to f of x and mod f n's are all bounded by some fixed constant, right. This is true for every n, that is what you mean by pointwise and bounded, and we denoted it by P b, right. Then we know that the operators T f n converge to T f in the weak operator topology, right. We showed that. In fact, it converges in the strong operator topology. So, we can strengthen that. So, let me write down that as a proposition. Okay. Proposition: if f n are bounded functions on sigma, okay, and f n converges to f pointwise and boundedly, then T f n converges to T f in the strong operator topology. Okay. So, we will use a second version of the spectral theorem. Okay. So, remember all these fn's are bounded functions. So, starting from A, which gave us continuous functional calculus, we had extended everything to bounded functions. So, for each bounded function on sigma, we have an operator, right, that is what we call T sub f, right, and that map had all the properties you want, except that when fn converges to f in the pointwise and boundedly, we could only prove that it converges in the weak operator topology. Now, we can extend it to the strong operator, I mean we can strengthen it, so that it converges in the strong operator topology. Okay, so, let us see why. This is because of the spectral theorem. Now, if you look at what we have done, each, so I will be very brief here, each fn T sub fn is actually a multiplication operator by fn, right, that is what. So, up to unitary equivalence, T fn is multiplication by fn. So, T fn is the operator which is the multiplication by fn on L2 of omega f mu, right. So, remember that the Caesar algebra A is identified as multiplication operators. Here we are talking about bounded functions, right. So, you have to sort of extend that to all bounded functions, but that is a trivial step. Okay. So, all the TFNs, so from A identified with C sigma, we went to large algebra, right. So, maybe it is a good idea to write it down. So, A was identified with C sigma, that is the Gelfand-Naimark, and then we went from C sigma to bounded functions on sigma, and we got this corresponding algebra T sub f, right, f in bounded functions on sigma, right. This map also had the same property, that it was an algebra homomorphism and so on. Okay. So, and the spectral theorem says that this can be identified as, A can be identified as multiplication by operators on an appropriate L2 space, and so by taking appropriate limits you will get the same thing for this algebra as well. Okay. So, I am not going to write down the details, but that is a straightforward argument, we have done this several times by now. So, up to unitary equivalence TFN can be viewed as multiplication by Fn on L2 of omega Fp. Okay. So, T sub Fn, so I will identify T sub Fn and its unitary copy, that is U T sub Fn U inverse, right. So, I will simply write U Tfn. Okay. So, Tfn acting on phi is Fn times phi, right, where phi is in L2 of omega f, right. That is how your operator looks like now, and you want to show that Tfn converges to Tf in the strong operator topology, provided that Fn converges to F in the point is pointwise and bounded. Okay. So, let us do that. This is a easy consequence of the dominated convergence theorem. Okay. So, Fn converges to F pointwise and bounded. So, since Fn converges to F pointwise and boundedly, we have, well, first of all Fn times phi, phi is in L2 not bounded, but Fn phi will converge to F phi pointwise, right, and Fn's are converging to F pointwise and boundedly. So, all the Fn's are going to be bounded by some fixed constants, right. So, mod Fn phi is less than to some constant times mod phi, which is in L2, right. So, this is in L2, L2 of course omega f. Okay. So, now just to show that Fn phi Tfn converges to Tf. So, if I look at the norm of Tfn acting on phi minus norm Tf acting on phi, right, L2 norm, right. To say that TFN converges to TF in the strong operator topology, I acted on a point phi which is in the Hilbert space L2 and then show that TFN phi converges to TF phi in the Hilbert space, that is in the L2 norm, right. So, L2 norm square is equal to mod Fn minus F square mod phi square dV, right. So, mod of Fn minus F square, that goes to 0 because Fn goes to F, right. But all of them are bounded by some constant, right. Fn's are all bounded by some constant, F is also bounded by the same constant. So, mod Fn minus F is going to be bounded by some 4 times that constant square, right. So, mod of Fn minus F square is less than to some fixed constant, let us say k, and mod Fn minus F goes to 0, right, as n goes to infinity point wise. So, I have that mod phi square there which is in L1 and so this will go to 0 by dCt, right. So, pointwise and boundedly converging will give me convergence in the strong topology, right. So, hence TFN converges to TF in the strong operator topology. Strong operator topology. Okay, so, we have strengthened our observation that TFN converges to TF in the weak operator topology, but now we have convergence in the strong operator topology and so everything now sort of identifies with whatever we have done earlier, right. So, we had the strong convergence when we did things earlier, but when started with projection valued measure and so on, when we developed the L infinity calculus, we had only weak operator topology convergence. Okay. So, we have some more time. So, let us now restrict ourselves to the case of a single operator. Okay. So, now we consider the case of a single operator. Okay. So, instead of looking at an algebra of operators, we will look at a single operator and of course, look at the algebra generated by that operator. Okay. So, let T be a bounded operator and normal. Okay. So, remember what is normal? T commutes with T star. So, T star T equal to T T star. Okay. Let A be the C star algebra generated by T, right. So, T and T star commutes. So, it will be a commutative C star algebra. Let A be the commutative C star algebra generated by T, T star and of course, identity, right. So, you look at the so called this so A, sometimes we will also write C star of T. Okay. So, that is the C star algebra generated by T. So, just another notation, but you can keep A in mind. So, let A be the commutative C star algebra generated by T, T star and LT. Now, we have already seen that then we know that the spectrum of the algebra, spectrum of A can be identified with spectrum of the operator T itself, which is a subset of the complex plane, right. It is a compact subset of the complex plane. Okay. But let me remind you how this is done. So, because that is important, because I need to look at the Gelfand transform of T and see what it is. Okay. So, sigma A can be identified with sigma of T and how is it done? So, recall that this is done by So, you take any phi in sigma of A. So, that is going to be a multiplicative linear functional on A, right, and you evaluate it at T, right. So, phi of T, so this is going to be a complex number, right. So, phi going to phi of T. So, phi of T is actually the Gelfand transform of T evaluated at phi, right. So, that is the map, right. So, this is coming from sigma of A and this is inside spectrum of T, right, and this is how it is identified, right. So, this map is a homeomorphism because the algebra is generated by T star and identity, and if I know the value of phi at T, I know the value at T star because it is simply the complex conjugate, and I know the value of phi at all points, and that is how the homomorphism was proved, right. So, sorry, the homeomorphism was proved. So, we are able to identify sigma A as a compact subset of the complex plane. Okay. So, in other words, and then we had the Gelfand transform, right. So, if I take any T in A, well, so instead of T let me use S because T is our fixed operator we started with, right. So, single operator T. Okay. So, if S is in A, then S hat, this is the Gelfand transform of S, this is a continuous function on the spectrum, right. So, this is how it is, and let us see what is the Gelfand transform of. So, what is the under this identification, what is the Gelfand transform of the operator T? Okay. So, let us identify these things again. So, for each sigma element in sigma A, I have some number or a point in sigma, right. So, if I take a lambda here, so that is a point in the complex plane, right. Remember this is sitting inside the complex plane. I have a linear functional, right, multiplicative linear functional phi lambda, and similarly if I take a phi here, I have a number sigma which is there, right. So, this identification is what is the homeomorphism is. Now, what is the Gelfand transform of T? So, I will have to look at T hat of lambda, right. So, what is T hat of lambda? Well, T hat of lambda is going to be T of phi lambda, okay, or T hat of phi lambda after the identification equal to, well, T hat of phi is phi of T, right. So, this is phi lambda of T, right, which is equal to, well, you look at this picture here, any phi is identified with, so phi is in the spectrum of A and that is identified with the point in the complex plane by looking at phi of T, right. So, I am looking at phi of T, right, and that is of course, phi lambda is identified with lambda, right. So, I will get lambda. So, the Gelfand transform of this operator, this is the operator which generates your sister algebra, right. So, the Gelfand transform of this operator T is simply the function lambda going to lambda on the spectrum, right. So, after the identification of sigma A with a subset of the complex plane which is the spectrum of T, the Gelfand transform of this operator T is simply the identity function on the spectrum of T. Okay. So, that is what you should understand. So, T hat is identified with is the identity function that is I lambda equal to lambda, okay, not a constant function 1, okay, that is the identity in the algebra, right. The identity by identity function we mean lambda going to lambda, okay. Now, the Gelfand, so now everything should be clear to you that once this is clear. So, see if I have the algebra A and it is supposed to be identified with sigma, right, C sigma. So, how is this done? So, I take the operator T here. So, let us see this picture. So, I take the operator T. So, this goes to the function lambda going to lambda, right, that is my continuous function there. Where will T square go? So, Gelfand transform is a algebra map, right. So, T square will go to lambda going to lambda square, right. So, that map, right, that is the continuous function on the other hand side. Where is T star going? Well, T star goes to, because the Gelfand transform is a star homomorphism, the star on A should go to the star on the other side, right. Star on the other side is the complex conjugation. So, that is lambda going to lambda bar, okay, and so on. So, if I take any polynomial, let us say in T and T star, because T is normal, T and T star does not matter how you write this, and the polynomial makes sense, that is going to go to the function which takes P to lambda lambda bar, right. So, in other words, if I look at let us say T square T star cube, this will be mapped to lambda square into lambda bar cube, because it is a algebra homomorphism and star goes to star and things like that, right. So, from here now you take the norm, right, you use the norm and take the closure, right. So, you do the closure with respect to the operator norm, that is what will give me the A, right. And here I have polynomials, on the right hand side I have polynomials in lambda and lambda bar. So, Stone-Weierstrass theorem will tell me that if I take the closure with respect to the supremum norm, I will get all continuous function, right. So, closure with respect to the supremum norm gives me C sigma, right. So, that is the Gelfand transform. So, now this should be perfectly clear to you what is happening, right. If I start with a normal operator T and look at the C-star algebra generated by T, the Gelfand transform identifies A with C sigma in this manner, right. T is identified with the identity function lambda, lambda going to lambda, and T square will of course be identified with lambda going to lambda square, T star goes to lambda bar, and so any polynomial in T star will go to the corresponding polynomial in lambda and lambda bar, and then you take the closure with respect to the operator norm on one side, the other side because it is an isometric isomorphism you will be taking closure with respect to the supremum norm, right, and so you will get A and C sigma. So, this is essentially Gelfand-Naimark written in a somewhat neater way, so that it is clear. Okay. So, we will stop here, we will continue from this point and look at the case of the single operator in a much more detailed manner. Okay. So, let us stop here.